Let's talk about polar coordinates. If we let's go off of a topic that we are familiar with. If I asked you, we'll do this with an easy one initially. If I asked you to go from 0, 0, okay, which is point A, and wanted you to get to this point right there, how would you travel to get there? You would? Then tell me, so if you're going to travel diagonally, then tell me the directions that you're going to take. Okay, so you're going to travel what we say to be rectangularly, okay? Because you're going to move horizontally 3 units to the right, followed vertically by 3 units up, right? And that intersection of moving that way, let's see if I still have this from last period. So if you wanted to move from J to K, the origin to this position in two-dimensional space, okay, you told me that you would move 3 right, 3 up, right? And because of the way that this movement here interacts with that movement there to create a right angle, we call this a rectangular movement, rectangular coordinate system, okay? And we know that we can go to J to K a lot of other different ways. I can go up 3, right 3, couldn't I? Would that still be rectangular? Can I go up 1, right 2, up 2, right 1? Yeah. But every movement that I make there, up 1, right 2, up 2, right 1, every transition happens at a right angle, correct? Okay. And collectively, the amount of movements that I make to the right would still have been this 3 here, and the amount of movements that I would have made up would still have been that 3 there, right? Okay. A lot of times people refer to the rectangular coordinate system as taxicab geometry, okay? Meaning that if I want to go from J to K, and I'm in New York City, I want to go from J to K, the dotted lines up there, the grid lines, are your roads, and the areas between those, the yellow regions essentially, are properties that I cannot drive through. Does that make sense? So I can only move left, right, up, down. Okay? That's called a rectangular coordinate system. All right? How many, what is the total amount of distance that if I'm at J and I want to go to K, what's the total amount of distance using the rectangular coordinate system that I realize there? 6 units. Okay? 3 right, 3 up. Okay? There's a more efficient way to go from J to K. The more efficient way from J to K is to move rectangularly. Or sorry, not right. Diagonally is what I was looking for. Yes, sorry. And we don't even call it diagonally. We'll talk about what we call it here in a moment. But I want to go from J straight to K. So what would I actually be traveling along here if I go J to K? A hypotenuse. Good. Okay. But that hypotenuse, okay, is going to be how big? Square root of 18. Everybody okay with that? Now, what that means to me is if I were to take a segment, not sure. All right, let's do this. So you told me so this distance right here would be square root of 18. Okay, that's what that is right there. Okay. But if I go square root of 18, I say, hey, you're going to start at A. Let's say all of us are going to start at A, and I tell you to walk square root of 18. That's all I tell you. Could we all end up at different spots on that circle? Yeah. We don't want to end up at different spots, though. We want to end up at K. I want all of you to go from J or A straight to K. So I need to tell you an angle to rotate yourself. So what we're going to do is that we're all going to start facing the positive x-axis, okay? And then I'll tell you an angle that you need to rotate, so that you start facing this point that we're going to get to. Okay, so what would that angle there that you'd have to rotate? 45 degrees in this case, right? And then I say, once you've rotated 45 degrees, now walk square root of 18 units, and it's going to put you right there where we want it to be. Okay? The square root of 18 distance is the what for that circle? The radius. And that 45 degrees or pi over 4 is an angle, right? It's a theta. Okay? So I can give you directions to get to that point on that circle two different ways. I can tell you start at the origin, move right 3, move up 3, and you get there. But you've now exhausted, if we're talking, let's like talk about, you guys probably talked about like forces and stuff like that in physics, right? Okay. Let's just talk about energy in regards to, walking like a mile. You've just wasted a bunch of energy because you walked 6 miles, right? If I go from A to K, okay, that point on the circle, and I say do it by traveling radical 18 at an angle of 45 degrees, now you've walked 4.24 miles instead of the total of 6 miles. Does that make sense? So we call this polar coordinates. Polar coordinates are more efficient to move around in the coordinate plane, or I want to say coordinate plane, in the two-dimensional plane, rather than moving rectangularly. Okay, rectangularly are they make more sense to us, I think, and it's more natural, and that's why obviously you learn rectangular coordinate system like 7th grade, 8th grade, 9th grade. Try to think about some of the stuff that we do right now might be difficult. Try to think about doing some of this when you're a 7th grader and understand why they don't introduce polar coordinates until you're in 11th grade, 12th grade student. But they are more efficient. Okay, they are. I don't want to say cleaner, but they're in certain applications they are better than rectangular coordinates. Rectangular coordinates sometimes we get kind of stuck with certain situations. Okay, polar coordinates don't allow that. Okay, so you saw me at the beginning of class trying to draw something. I don't know what I did with it. There it is. Okay, that image, very difficult to draw, to graph. That is a graph, and it's very difficult to graph using rectangular coordinates. We can do it. Okay, you guys ever heard the word parametric equations? Okay, you get to calculus, you might do some parametric equations. Basically what it is, a parametric equation, it's an equation that gives you a location on the x-axis, and then it gives you, it's a second equation then that gives you a y value. So there's a parametric equation is two equations, one's on x and one's for y. And where they intersect then is a point. Does that make sense? Okay. Then we use a third variable called t, which is the time, and basically as the time moves along, the x's and y's change off of that third variable, and if we trace the point, then it creates a graph. Okay. See if I can give. I'm assuming Desmo's probably somewhere. Maybe it's already built in. See if we got anything parametric here. All right, so, and it's not written the way that I want it to be written. I don't like that either. One gives a structure to find the X position. One finds a structure to find the Y position. So if I were to look at maybe that point right there, in parametric equations, one of the equations gives me that line right there. The other one will give me that line right there. Does that make sense? But they're based off of a t value, a time value. And as that time value starts to oscillate between predefined values, what's going to happen is that those equations change. And they would be maybe become that set of lines, or they become that set of lines. And as I trace and change t and trace point B, what's going to happen is I trace out that image. Okay? So parametric equations will allow us eventually to make certain graphs like this. Okay? But this is much easier to graph using polar coordinates. Okay? Do you guys know what a Cnc machine is? We talked about this a couple weeks ago with Grobe. Okay? Let me show you real quick with just a YouTube video here real quick. Find a... All right, so Cnc machine is it's a router, it's a carving tool, and it's programmed to you put down your piece of wood or aluminum or whatever. There's a lot of different versions of CNC machines, but you program it then with something that's called G code that tells this thing how to move on these axes. Okay, you'd have to get into the code and all that kind of stuff to realize this or see it. But what it does is allows you to make things that are very precise images, text, but it's making this thing move to create those. Does that make sense? Okay. So this stuff gets very, you can get very intricate with it. You can see, this guy's making. Like he's got his machine cutting all this stuff out and making these very detailed images. Does that make sense? Okay. That'd be very hard. I'm making the assumption that'd be very hard to get the programming done using X and Y parametric equations. Okay. And maybe they do, but I would argue that getting that router to move in two-dimensional space, like it's actually three-dimensional space, probably uses a little bit of polar coordinates. Does that make sense? Because it's more efficient, it's easier. I could be completely wrong, but it allows the graphing of the creation of something like this to take place. Okay, that'd be very hard to come up with an algebraic X and Y rule for this curve. Does that make sense? Okay. And we could do a lot of things. If I just take and change this to like a 2, change it to a 3, so change back to a 4, you can see the different things that happen. Maybe I change that to a 5 or a 55. There's a lot of different things that you can do and create using these parametric, not parametric, polar coordinates. Okay. So basically what this is a rule right now to tell me the radius of a circle, okay, and then it captures it runs through our theta between 0 and 2 pi, and it just plots this. When I choose theta to be, let's say, 0, it calculates all this, finds that r that goes with that, and then plots against it 0. And then if theta is pi over 6, it plugs pi over 6 through here, evaluates that, that's my r, and then comma pi over 6, and it plots that point. And if you do that all the way from negative infinity to positive infinity, this is the curve that gets made. Okay. We won't talk about too many things that are this intricate, but we will start talking about some polar graphs in the future that are kind of the basics of that. So when we talk about polar graphs, okay, and we want to go from, like I said, we were trying to move from this point to that point, but we don't want to move horizontally and vertically anymore. We need to move on a circle, okay? So there's a lot of circles. Okay, these would be all the different circles that we could put in there, right? Okay, if I let this go to, I can put all these different circles in here. And if I were to highlight them, see if I can do that. Highlight all these different circles, okay? You could now tell me, and I graph the kind of like our X and Y axes, okay? Okay, if we just had our X and Y axes, it's hard to move, 7 units to the right. So what we do is we take our X and Y axes and we say, okay, chunk off what a distance of 1 looks like, and then replicate that 7 times, right? And now I can move to the right 7 units. Same idea here. If I told you to move at a radius of radical 18, that's going to be hard to do, okay? But if I start looking at what, a radius of 1 looks like, a circle with a radius of 2, a circle with a radius of 3, a circle with a radius of 4, then I can have an idea of how far radical 18 needs to be. Does that make sense? So we look at also basically in a rectangular, we have X and Y axes, and then we have what we call major and minor grid lines that are vertical and horizontal lines, right? Same thing happens in the polar coordinate system, except for now, instead of vertical and horizontal lines, we have circles intersecting with rays, okay? So those circles then are what we're going to look at. Then we're going to look at rays that are passing through pi over 6, pi over 4, pi over 3, pi over 2, and when we put those things together, what we end up with is this image. It's kind of a pain in the butt to find where you toggle back and forth between polar and rectangular. There we go. To go to grid, we're going to go down to grid type, click on polar. I'll make my lines darker for you so we get something like that. Okay, so instead of the vertical and horizontal lines intersecting rectangularly, we get these concentric circles, and then we get these rays. Usually you'll see, if you were to Google polar graph and go to Google Images, a lot of times you're going to see a lot more rays than what we have up here. These are all at 30 degrees. What you usually see on paper is multiples of 15 degrees. Okay, so they're in pi over 12 increments. But so this is 30, so then you'll see it probably another one about right there. So the idea then is if I wanted to go, so when I type in 3, 3 here using GeoGebra, because I use a comma, GeoGebra is coded to say when user enters comma, user is dealing with rectangular coordinates, okay? So what they're saying, even though I've got the polar coordinate system overlaid here, what they're saying is still move to the right 3 units and then move up 3 units. Does that make sense? Okay, so we get that point. But if I go, I want to go, we said a radius of the square root of 18. Follow that up with then at an angle of 45 degrees. Okay. Now if I type it that way, it does not put the point on top of A. So I know I've done this incorrectly because I used a comma. Again, GeoGebra is saying user uses comma, so we're talking rectangular coordinates. So it wants me to move, 4.2 units to the right, which is square root 18, and then pi over 4 is about 0.9 probably 0.7 up, okay? Well, I don't want to do that. So when you put a semicolon there, now it says user is talking about polar coordinates. And if I put a semicolon there and hit enter, does it put that point B right on top of point A? So right now, if I go over to the algebra view of this, these two things are directions to get to the exact same point in two-dimensional space. Okay, so if I want to go from, I'm just going to put that point right there, point C, and I'm going to hide my axes and I'm going to hide my grid. Okay, and if I told you to go from C to point B, point A, but there was no grid up there, okay, how are you going to do it? How am I going to give you those directions? It's going to be kind of hard, right? Okay. If I put in those, and we use rectangular systems, I can say, move right 3, up 3. And you get there, right? Okay. Or I can put that in, and I say, move at a distance of radical 18 at a 45-degree angle, and you get to the same exact point. Does that make sense? Okay, so I like to think about it as, you know, like I said, if I'm going to start a problem about going from one spot to another, I like to think about my rectangular system being on a transparency. Okay, my X and Y axes and the grid being on a clear piece of plastic. And then I have the polar one on another piece of clear plastic, right? And I'm just going to slide them. I'm going to slide the origin on top of C, or then I'm going to slide what we call the pole on top of C, and then I now have a system that allows me to relate C and B or C and A to one another, and I can create directions to get there. Does that make sense? Okay. What I want you to understand is we're not doing anything new here. We're not creating a whole nother, remember when we talk about points, they're locations in space. Locations and we're talking about two-dimensional points, locations on a two-dimensional surface. I'm just telling you how to go from one to another using two different sets of directions. Okay, so these two things relate to the exact same point. When we get into graphing points on a polar system, there's a lot of things that are similar to the rectangular system. When you first learn the rectangular system in 7th grade, 8th grade, Algebra 1, you talked about the structure and some names of certain things on that graph. You talked about the x-axis, you talked about the y-axis, and you talked about the origin, and then you talked about the quadrants, right? You identified those things first. So there's a couple things like that, okay, on this system. The first one is that point right there, which would be analogous to our origin. We call that the pole. Okay? Think about this. If you were to look at a globe, put the globe on the floor, stand above it, your lines of latitude all come together, and the smallest line of latitude is a dot at the North Pole, right? Okay? This ray right there, okay, called our positive x-axis in the rectangular system, right? We call that our polar axis here. Polar axis. Okay, those are the two structure parts of a polar graph that we'll refer to. When we talk about an angle that they give us in our polar coordinates, the angle is interpreted, if it's positive, we're moving counterclockwise, like we have been all course. Okay? If it's negative, we're moving clockwise. Okay? Does that make sense? So, and they can give it to us in degrees, or they can give it to us in radians. But if they ask me, so every point is going to be an r comma theta. And if you're a person that wants to, like if you put semicolon here, I don't care. That sometimes, depending on what theta is in, sometimes they'll give you theta in degrees, and it's really easy because you got a degree symbol. You know that it's talking about a polar coordinate, okay? But if I gave you this right here, and let's say that we're in, I don't know if I can change it on GeoGebra. Okay. Well, it puts RAD. A lot of times they'll put like 4.2426 comma 0.7854, and they won't put the RAD and they won't put a symbol. That would look a lot like a coordinate, a rectangular coordinate, wouldn't it? Okay. So there will be times where that happens, where you're provided something that they say in the directions is polar, but it looks a lot like a rectangular coordinate. Okay. So if you want to put a semicolon when you write these things, there's nothing wrong with that. I'm fine with that. Okay, it allows you to distinguish, is it rectangular? It's an added feature that allows you to distinguish if it's supposed to be rectangular or polar. But we go R theta. Okay, the first question up there says graph R to be 3, theta to be 315 degrees. It does not matter which of those that you deal with first, either the 3 or the 315. Kind of like when we graph x comma y. We learn and try to get trained to do the x first followed by the y, right? But I have students that do the y first and then they move over to x. That's fine. It gets you the same spot, right? Same thing here. But I prefer, just as a personal opinion, I prefer to go 315 first. Basically what I'm going to do is I'm going to start on my polar axis. I'm going to start right there. And I'm going to rotate counterclockwise 315 degrees. If I rotate counterclockwise to 315 degrees, I'm going to get right there. Does that make sense? Okay. So I'd be somewhere. So this point is somewhere on that ray. It's now the intersection of the third circle in that ray. So I'm going to go find the third circle. 1, 2, 3. And that point right there is 3, 315 as a polar coordinate. That's pretty simple, straightforward to do. Find the terminating ray and then count out what circle on that terminating ray that you're interested in. The next one is 2, 45. So 2, 45 would be, there's my 45-degree angle. I'm going to count out the second circle. So it'll be right there. Now, just like anything else, you know, if they asked me to go 2.5, 45, I'd have to guess where 2.5 was, right? Because I've only got circles at 2 and 3. One thing that's a little bit different is the idea of negative 2 pi. So if I want to go negative 2 pi, this is point C up here. Negative 2 pi, okay? And this is the reason I always like to go with the angle first. If I want to go pi, okay, so I start on my polar axis. I'm going to rotate counterclockwise out to pi. So I should be on that ray right there. Does that make sense? Okay. Does anybody, I mean, if I go out to, what does it mean to go to negative 2? Well, that would be positive 2, wouldn't it? Does that make sense? So negative 2 is not on this ray. Negative 2 is actually on the opposite ray. I would go out to there. Okay? So that point right there is negative 2, pi. Okay? Whenever your R value is negative, you're gonna travel to the angle in the terminating ray as you always would. But if your R value is negative, you then travel in the opposite direction that many units. Does that make sense? Okay. Now here's my question to you. Is there a better rule or set of direction? If you're starting here at 0, which is the pole 0, comma 0, in regards to R and theta, if you're starting there, what would be a better way of getting to there? 2 comma 0, right? Does that make sense? So let's see something here real quick. Let's go to GeoGebra. If we put our polar coordinates back in, okay, and I just ask it, what does negative 2 comma pi look like? It's that point right there. Okay. You said, why not just go 2 comma 0? Gives me the same point. Okay. Now, GeoGebra auto fixes it for me. If I type it in, you see that that was negative 2 pi, right? That was 2, 0. Did it plot on top of the same point? Okay. So that's where it's different. That's a unique thing with the polar coordinates that's different than the rectangular coordinates. If I tell you 3, 3, go to 3, 3 or 3, 5 in rectangular coordinates. There is only one way of expressing how to get there, 3, 5. But if I want you to go to that point A up there in polar coordinates, there's an infinite number of ways of doing that. And it's infinite because of the way that I can start at A, and if I want to travel 360 degrees again, do I get back to A? I can travel 360 degrees again and get back to A, right? Coupled with the idea of being able to maybe start with a negative R value, okay, gives me even more than infinite. I guess we get 2 times infinity in regards to the number of different ways that we can express an ordered pair in polar coordinates, okay? That becomes an issue because I could ask you, identify this ordered pair as a point, and I could have 25 different answers that are all right, correct? So what a lot of times they do is they say, we're going to do this. We're going to understand that there can be an infinite number of ways of identifying an ordered pair, but technically what we like to do is we like to keep our R value positive, and we like to keep theta between 0 and 360. Okay? If we keep those conditions, then everybody's going to have the exact same directions to get to the exact same spot. Okay? But that's not saying that in your homework and stuff like that, that they might target questions of moving with a negative theta or a negative radius. Does that make sense? All right. Tomorrow we'll pick up more of this. We'll do we'll graph the rest of these. We'll get into how to, if I give you 3, 3, let's say I give you like the point 5, 2. How do I convert that over to a polar coordinate? Because every rectangular coordinate has a polar counterpart, and every polar coordinate has a rectangular counterpart, and we'll be able to jump back and forth between the two. And that's what we're going to do tomorrow. No new homework. I'm going to post, hopefully, 6th period, your Chapter 7 test online. You'll have a week to do it. Shouldn't be anything that is extremely taxing for you.